we're going to now talk about tying up loose ends to the extent that we can in this lecture. Let's talk about this one first, another loose end. What about theta equals 0? Okay, I'm going to talk about this more in words rather than writing anything. If you want to see it a little bit more detail, you can check the notes. Well, okay. If theta happened to be literally 0, then 1 over theta is infinity. And indeed, this loop would loop forever. Like k times theta would never get up to medium. So, of course, in real life, you would not let this run forever. At some point, you would be like, all right, I'm stopping. So you could instead have this run up to some, largest possible value, k max. Let's up here, like maybe stop it at k max, which you choose, some big power of 2. And if it gets all the way to the k max and doesn't, detect mediumness, then let it return like a different phrase. In this case, let it return theta hat is, well, let it return the phrase, I think theta is less than 1 over k max. And you can show that by similar part 1, part 2 analysis, you can show that this is still kind of a correct algorithm in the sense that if the algorithm gets this far and returns that theta is smaller than 1 over k max, then that's true. Theta is smaller than 1 over k max. Because if it was bigger than 1 over k max, then this part 2 analysis would have told you that you would have stopped. And on the other hand, there's still like a little gray zone issue here, but on the other hand, if theta is less than 0.25 over k max, the algorithm will return this. Okay, so again, like if theta is right around 1 over k max, maybe it'll halt here, or maybe it'll detect that exactly. But anyway, if it says this, that's true. And on the other hand, if it really is smaller than 1 over 4 k max, then it will say this. And if it ever comes to this, in this case, the number of mystery rot calls is order k max, because this will be k max. Okay, so like it's kind of like an addendum to this factor-2 estimate that if you pick your cutoff point k max, then you know for sure it'll never take more than this many calls. And moreover, like it has this bonus feature that it sort of detects this edge case that theta is smaller than 1 over k max. And this is useful in application. So if you were going to use, if you were back in the Grover SAT scenario, you would exactly do this with like taking k max to be 1 over square root of 1 over 2 to the n. So why do I say that? Well, in Grover's setup, P, you have this P, which is the fraction of satisfying strings for your n input, 1 output function. And you kind of know that P is either at least 1 over 2 to the n, if there's one satisfying string, or it's 0. And so once you kind of figure out that P is smaller than 1 over 2 to the n, you've sort of automatically figured out that P is 0. You don't, so that's good. And so that smallest possible value of P, like 1 over 2 to the n, if you remember, theta, the angle, is like 2 square root, no. Yeah, 2 square root P. So that sort of smallest possible theta is like square root of 1 over 2 to the n. So in the Grover application, like this is like the smallest angle you ever care about. And if it's smaller than that, you're like, oh, it's 0. And that's nice because that means you can set Kmax to be this, and your final sort of upper bound on work is square root of 2 to the n, which was, the initial headline running time for Grover's algorithm for set. Okay, so let me leave it at that. Okay. Now let's focus. Let's talk about this loose end, this temporary pretending. Okay. So the issue here was we analyzed this is medium algorithm, and we saw that actually it can occasionally give like a blatantly wrong answer. And the probability of it giving a blatantly wrong answer is at most 10%. And then we were like, let's just pretend it's 0%. Now, we got to fix this. So the fix is like a well-known fix in randomized algorithms that doesn't have anything to do with quantum. It's the same thing you always do if you have like a algorithm that works with high probability and you wish it worked with really high probability. You basically repeat it a bunch of times. So for example, on this reliability issue, here's an idea. Instead of just calling is medium once in this factor-2 estimate, call it 3 times. Okay, and it'll give back 3 answers, like yes, no, yes, maybe. And in this case, you're like, well, twice it said yes, so let's go with yes. So like overall, take the majority answer. So this 3 times boosted version of is medium, it works with even higher probability. Because what's the probability that this thing is wrong? Well, the worst case is that like is medium really works with probability exactly 90%, and it gives you the wrong answer with probability 10%. So how is this overall algorithm wrong? It's wrong if it gets like 2 wrongs and a right, or if it gets 3 wrongs. So the probability of all 3 wrongs is like 0.1 times 0.1 times 0.1. It's actually at most that. And the probability of 2 wrongs and 1 right is, well, you can be like wrong, wrong, right. 0.1, 0.1, 0.9, or you can be wrong, right, wrong, or you can be right, wrong, wrong. So this is the probability of overall wrongness. And if you add this up, it's 0.028, which is like 3%. So you're like, oh, I used to have failure probability 10%. Now failure probability 3%. It's even better. And if you're like, oh, but now I want even lower probability of failure, well, you can repeat it 5 times and take the majority, or 7 times, or 9 times. Or I'll just tell you, this, by the way, is smaller than 2 to the minus 3. And I expect that probably in some probability or statistics course, you've studied this exact, or actually course that talked about randomized algorithms, you've talked about this exact scenario. And there's something called Chernoff bounds. It's kind of similar to the central limit theorem, but I'll take it as a given, this probabilistic or statistical fact. It's called Chernoff bounds or large deviation bounds or something like this. That if you repeat this algorithm, like is medium or any yes/no algorithm, if you repeat it t times and take the majority answer, the failure probability becomes less than 2 to the minus t. Okay, we saw an example of that here with t being 3. Okay, so take my word for this. And I guess it's also sort of like problem 6 on the homework. And this is a great situation because this is an amazing trade-off for you. You do 10 times more work, the failure probability is like 1 in 1,000. You do 100 times more work. The failure probability is like unbelievably tiny, like microscopically tiny. Okay, so I'm going to make a definition. This is like somewhat non-standard, but like let's say a probabilistic algorithm works with overwhelming probability, abbreviation WOWP. It's kind of non-standard, but we'll say that. If it has this feature. Okay, or by this, I mean, this. But basically, you can boost its probability by like repeating it t times and taking the majority answer or the median answer or some correlation of the answers, and the failure probability goes down exponentially fast. Let me throw a big O in here, actually. Okay, and now, although it like 1% breaks my math-loving heart, I'm going to give you some license to cheat a little bit. So this is a special license I grant you. Whenever you have an algorithm that works with this overwhelming probability property, I personally grant you the license in this course to pretend it is deterministic, that it works always. Okay, so that's my special gift to you. Let me say with, I should say, with constant factor slowdown. Okay. So why is this okay, morally speaking? The reason it's okay, morally speaking, is you could set t to be, you could just take this and fix t to be 200. Okay, if you take t to be 200, then it's true, you have to call is medium 200 extra times. Every time you plan to call it, okay, maybe it should be odd if you're going to take the majority, but let's say 200 extra times. And you're like, that slows down the algorithm by a factor of 200. But okay, that's a constant factor, and we can put that into the big O. But then the failure probability is less than 2 to the minus 200. And I'm here to tell you 2 to the minus 200 is 0. Again, it's cheating a little bit, but I looked it up. If you measure the age of the universe in time units called Planck times, which is like, according to, I don't know, quantum field theory, the theoretically least amount of time that exists. Apparently time is discrete like that. The age of the universe in this number of Planck times is less than 2 to the 200. So it's like basically like an event that occurs with probability 2 to the minus 200 will never ever occur ever in the world. And so it's sort of genuinely fine to pretend that it's 0. I mean, it's infinitely more likely that like an asteroid will just crash into your room that contains the quantum computer. So if you're really a math nerd, you're like, oh, I'm going to check how many times I might need to take t to be like log n, and that'll make the failure probability smaller than 1 over n, and then I can use this pretend n times with union bound, but I don't want to get into that. So whenever we encounter an algorithm with this property, I'm going to cheat a little bit by just pretending it always works. And morally speaking, it's not a cheat. Okay, this is really just to like omit some tedium. Okay, one more loose end, which is this one. And since I have like 4 minutes, I'm just going to sketch how to handle this loose end, because anyway, next lecture, we're going to drill into this one for like the whole lecture. So let me just sketch what will happen then. Okay. So at the end of the algorithm that we actually analyzed, the end of this factor-2 estimate, we know a power of 2, k, such that mystery rot repeated k times has a rotation angle between 22.5 degrees and 67.5 degrees. A nice medium angle. Okay. Moreover, we know the value of theta that we're trying to get up to a factor of 2. So we know that k, what do we know? We know that k theta is approximately 45 degrees up to a factor of 2. Okay. So what we're trying to do is, let me call this theta prime. So we know theta prime is sort of within factor 2 of 45 degrees. And I claim it suffices now to refine the estimate and figure out theta prime to within 1%. Because if we figure out theta primes within 1%, then we're just going to divide by k, and that'll give us a 1% approximation of theta. And I should estimate that these are all like relative errors. So we'll get like we'll get an estimate for theta prime, which is between, I don't know, 2 times theta prime and theta prime over 2. So now the point is, we have this medium theta prime. Draw this picture again. So we know how to make this rotation by theta prime, and we know that theta prime is somewhere in the neighborhood of 45 degrees. It's like between 45 degrees and 22.5 degrees and 67.5 degrees. And now we can do the thing that we did in is medium. We can just, rotate ket 0 by theta prime degrees, measure, and see if we get a 0 or 1. And do that like 100 times or 1,000 times or 1,000,000 times. And we'll figure out theta prime like really closely. We'll get this angle really close. And that'll be good enough, because now theta prime getting within, since theta prime is like a big chunky number, getting within 1% of theta prime is like getting within like 0.01 of theta prime. So that's what we'll manage to do. We'll figure out theta prime really closely, and then like within 1%. And then that will be a good estimate of, that'll be like a 1% estimate of theta, which is theta prime divided by k. Okay, so that's what we'll dig into next time. So see you then.